Okay, so the last thing we're going to look at before we take a look at reaction stoichiometries is this idea of combustion analysis. And you can think about combustion analysis as just being a twist on the normal determining empirical formula procedure that we've learned before. So just a reminder, when we're talking about combustion, we're usually talking about something that has some ratio of carbon, hydrogen, and oxygen. So I should just put X, Y, and Z to represent numbers, reacting with oxygen and becoming CO2 and H2O. And again, this is complete combustion where we have enough oxygen and we only produce carbon dioxide and water. Now, if you take a look, all of the carbon that we have in our reactant ends up in our carbon dioxide. All of the hydrogen that we have in our reactant ends up in the water, and then the oxygen gets sort of split between the CO2 and H2O. This is important because we're going to be using these masses to determine the mass of carbon, hydrogen, and oxygen. Now, in order to answer these questions, you need three different masses. You need the mass of the initial unknown compound, so the mass of your CHO, whatever ratio it is. You also need the mass of carbon dioxide and the mass of water. So we can take a look at an example where we have a compound that's only made of carbon, hydrogen, and oxygen, and you're given the three masses. So you have your mass of your unknown compound being 0.105 grams, the mass of CO2 and the mass of H2O are also given. Now the way that you set this up is exactly the same way as we did with empirical formulas. There's just one extra step at the beginning as a bit of a twist. So again, we take a look, we have carbon, hydrogen, and oxygen in separate columns. And again, the first thing that we need to do is we need to determine the mass of each of these because we're only given the mass of the compounds. So the first thing to do is write down the mass of CO2 and H2O. And then you need to take that mass and multiply it by the percentage of carbon that you have in CO2 and the percentage of hydrogen that you have in H2O. What does that mean? Well, carbon in CO2 is 12 grams out of 44 grams per mole of CO2, and hydrogen is 2 grams per mole out of the entire 18. So that gives you sort of a ratio, excuse me, of how much you have of each element within the compound. And so if you take that ratio, do the division, and multiply it by that mass, what you'll end up getting is the mass of only carbon within that mass of CO2 that's given to us at the beginning. So I'm doing the calculation here, I'm getting these masses. And then for oxygen, it's a little bit different. Instead of using that ratio of carbon in CO2 and hydrogen and H2O, what we're actually going to do is we're going to take that initial mass of the unknown compound and subtract the masses that we got for carbon and hydrogen. So here again, the initial mass is 105, and I'm subtracting the mass of carbon that I got from my first calculation, the mass of hydrogen that I got from my second calculation, and that'll give me the mass of oxygen. Okay, so this is the one sort of trick that you need to do before you continue with your regular empirical formula procedure. And again, this is only for when we're burning, when we have combustion analysis. So now that we have our masses, same deal as with our normal empirical formula process, we divide these masses by our molar mass of each element. So here I'm dividing by carbon's molar mass, by hydrogen's molar mass, and by oxygen's molar mass. I'm going to take a look at those numbers and determine the smallest, and then I'm going to divide by that smallest number. And again, in this particular section, it is important to try to keep as many decimals as possible because you want to try to get as an accurate number as possible. So even though I've only written, 7 here, I try to keep all of them on my calculator just so that I can get as accurate a ratio as possible. So again, here I'm dividing by the smallest, which happens to be the moles of oxygen. So I'm going to divide everything by 0.001933. And that should give me my ratio of carbon to hydrogen to oxygen, and I've therefore found out my empirical formula.